Calculating the common difference, d$, from a sequence. Welcome, everyone. Let's begin our lesson on calculating the common difference from a sequence. To start, let's take a quick look back at what we have already covered. In our previous lessons, we established the fundamental definition of an arithmetic progression, or AP for short. We learned that an arithmetic progression is a specific type of sequence where the difference between any two consecutive terms remains constant throughout the entire list. Because this difference never changes, we refer to it as the common difference. And in mathematics, we denote this value using the lowercase letter d. Now, as we move into today's topic, you might be wondering how to actually find this value. When you are presented with a list of numbers and asked to find the common difference, I want you to think of it visually. You are essentially measuring the gap, or the jump, required to move from one term to the next. In the next few slides, I will show you the precise mathematical formula to calculate this jump and how to apply it to various types of sequences. The mathematical formula. To find the common difference, denoted by the letter d, we don't just pick any two numbers. We specifically subtract any term from the term that immediately follows it. If you look at the center of the slide, you'll see the formal mathematical representation of this rule. It is written as d equals a sub k plus 1 minus a sub k. Now, don't let those subscripts intimidate you. Let's break down what they actually mean. The term a sub k plus 1 represents the succeeding term, which is just the term sitting at the next position in our sequence. The term a sub k represents the preceding term or the term that comes before it. This leads us to a very crucial rule that you must memorize to avoid errors later on. The subtraction must always be performed in this specific order: the succeeding term minus the preceding term. Why is this order so important? Well, as we will see in our upcoming examples, this specific order ensures that the sign of d, whether it is positive or negative, correctly tells us the behavior of the sequence. If the result is positive, the sequence is increasing. If the result is negative, the sequence is decreasing. Always keep this direction in mind as we move into the step-by-step process. Now that we understand that the common difference is essentially the gap between terms, let's look at how we express this mathematically. Step-by-step process to calculate d$. Now that we understand what the common difference actually represents, let's look at a practical, step-by-step process you can use every single time you encounter a sequence. To calculate the common difference from a given sequence, you don't need to guess. You just need to follow these 4 manageable steps. First, identify two consecutive terms. This simply means picking any two numbers that are sitting side by side in the sequence. While you can pick any pair, I recommend starting with the first term, which we call a 1, and the second term, which we call a 2, as these are usually the easiest to work with. First, identify two consecutive terms. This simply means picking any two numbers that are sitting side by side in the sequence. While you can pick any pair, I recommend starting with the first term, which we call a 1, and the second term, which we call a 2, as these are usually the easiest to work with. Second, apply the subtraction rule. This is where you must be very careful with the order we discussed in the previous slide. You will subtract the first term from the second term, which is written as a 2 minus a 1. Remember, always subtract the earlier term from the later one. Third, I highly recommend that you verify your result with another pair. To ensure the sequence is truly an arithmetic progression, repeat the exact same subtraction process using the second and third terms, which would be a 3 minus a 2. Finally, conclude the value. If your results from both subtractions are identical, then you have successfully found your common difference, d. If they are different, then the sequence is not an arithmetic progression. Let's move on to a real-world example to see this process in action. Now that we understand what the common difference actually represents, let's look at a practical, step-by-step process you can use every single time you encounter a sequence. Real-world example: water tank leakage. Now that we have covered the mathematical formula and the general process, let's apply what we've learned to a real-world scenario to see how this works in practice. Imagine you have a water tank that has developed a small leak. Every single hour, the tank loses exactly 4 liters of water. If we were to record the amount of water remaining in the tank at the start of each hour, we would generate a sequence of numbers. Looking at the screen, you can see the sequence starts at 100 liters, then drops to 96, then 92, and then 88, and so on. Let's use the step-by-step method we just discussed to calculate the common difference for this specific sequence. First, we need to identify our first 2 consecutive terms. From our list, the first term, which we call a sub-1, is 100. The second term, or a sub-2, is 96. Next, we apply our subtraction rule. Remember, we must always subtract the preceding term from the succeeding term. So, we take a sub-2 minus a sub-1. That gives us 96 minus 100, which results in -4. To be absolutely certain that this is an arithmetic progression, we must perform step 3, verifying with another pair. Let's look at the third term, a sub-3, which is 92. We subtract the second term from this third term, so a sub-3 minus a sub-2. That is 92 minus 96, which again gives us -4. Since the difference is consistent, we can reach our conclusion. The common difference, d, is equal to -4. It is important to notice that negative sign. It mathematically represents the fact that the amount of water in the tank is decreasing over time. Now, let's look at a few more purely numerical examples to reinforce this concept. Numerical examples. Now that we have understood the theory and the formula, let's put it into practice with our first numerical example. Take a look at this first example, which features an increasing sequence: 7, 13, 19, 25, and so on. Our goal here is to find the common difference. To do this, we will follow the step-by-step process we just discussed. First, we need to identify our first 2 terms. Looking at the sequence, our first term, which we call a sub-1, is 7, and our second term, or a sub-2, is 13. Next, we move to step 2, where we apply our subtraction rule. We take the succeeding term and subtract the preceding term. So, we calculate d equals a sub-2 minus a sub-1. When we plug in our numbers, that gives us 13 minus 7, which results in 6. But remember, to be absolutely sure this is an arithmetic progression, we shouldn't stop there. In step 3, we must verify this result using another pair of terms. Let's use the second and third terms. We take the third term, a sub-3, which is 19, and subtract the second term, a sub-2, which is 13. As you can see, 19 minus 13 also gives us 6. Since the difference remains constant, we can confidently conclude our result. The common difference, d, equals 6. Now, let's see how this same process works when the numbers are moving in the opposite direction in our next example. Numerical examples continued. Now that we have seen how to handle an increasing sequence in our previous example, let's look at a different scenario in example 2, which features a decreasing sequence. Our task is to find the common difference for the sequence: 15, 11, 7, 3, and so on. Let's follow the same systematic process we used before. First, we need to identify our first 2 terms. Here, the first term, which we call a sub-1, is 15, and the second term, or a sub-2, is 11. Next, we move to step 2, where we apply our subtraction rule. Remember, we must always subtract the preceding term from the succeeding term. So, we calculate d by taking a sub-2 minus a sub-1. That gives us 11 minus 15, which results in -4. To be absolutely certain that this is an arithmetic progression, let's perform step 3 and verify this with the next pair in the sequence. We will take the third term, a sub-3, which is 7, and subtract the second term, a sub-2, which is 11. Again, 7 minus 11 gives us -4. Since the difference remains consistent, we can confidently conclude our result. The common difference, d, equals -4. Notice how the negative sign correctly reflects that the values in this sequence are decreasing, just as we discussed in our earlier slides. In the next slide, I will highlight some common pitfalls to watch out for when performing these calculations. Common mistakes to avoid. Now, before we wrap up our lesson with the final summary, I want to pause and discuss some common pitfalls. Even if you understand the concept, it is very easy to make small errors that lead to the wrong answer. First, let's talk about the wrong order of subtraction. This is perhaps the most frequent mistake I see. Many students instinctively subtract the smaller number from the larger number, or they accidentally subtract the succeeding term from the preceding term, which looks like a sub k minus a k plus 1. Please avoid this. As we saw in our previous examples, the order is vital. For instance, in the sequence 15, 11, 7, you might be tempted to calculate 15 minus 11 and get 4. But that is incorrect. To get the right answer, you must subtract the preceding term from the following term, so it must be 11 minus 15, which gives us negative 4. Second, be very careful about ignoring the sign. It is easy to get caught up in the numbers and forget to write down the negative sign for decreasing sequences. I want you to remember this rule. If the numbers in your sequence are getting smaller, your common difference must be negative. If you forget that sign, your entire calculation for the rest of the problem will be wrong. Finally, do not fall into the trap of assuming that the common difference is always a whole number. While our examples today used integers, in more advanced problems, the common difference can be a fraction, a decimal, or even 0. Always perform your subtraction carefully and stay alert to the possibility of non-integer values. Keep these points in mind, and you will be well prepared for our final summary on the next slide. Key takeaways. First, remember that the common difference, which we denote in lowercase d, is that constant, unchanging value that we add to any term in an arithmetic progression to arrive at the very next term. Second, always keep this specific formula in mind. D equals a sub k plus 1 minus a sub k, as we discussed earlier in the lesson. The order here is vital. You must always subtract the preceding term from the succeeding term. Third, let's look at what the sign of D tells us about the behavior of the sequence. If you calculate a positive D, it means the sequence is increasing, just like in our first numerical example, where the numbers were getting larger. Conversely, if you find a negative D, the sequence is decreasing, much like the water tank example we looked at where the volume was dropping. Finally, there is a special case. If your common difference is exactly 0, then the sequence is constant, meaning every single term in the list is exactly the same. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing our key takeaways to ensure you have a solid grasp of this concept. If you have mastered these points and avoided the common subtraction errors we covered, you are well on your way to mastering arithmetic progressions. Great job today!